Let's illustrate the calculation of the safety index with a simple example. Here, a simply supported beam is shown, where we want to check the bending moment capacity at the midspan. The equation given illustrates the plastic flexural capacity of a rectangular section and the resulting bending moment at the midspan from a uniformly distributed load. First, let's use the partial safety factor approach. We want to design this simple beam with a breadth equal to 100 millimeters, height equal to 400 millimeters, and a length of 5 meters. The characteristic yield strength of the material is found to be 295 megapascal, and the characteristic uniformly distributed load is 320 kilonewtons per meter. The partial safety factor for the material is found to be 1.05, and the partial safety factor for the load is found to be 1.35. We use these values to calculate the utilization coefficient by dividing the design load by the design strength. In this case, the utilization coefficient is found to be 1.81, which is significantly higher than 1 and hence not acceptable. With some additional calculations, we find that the height needs to be increased to approximately 550 millimeters to achieve an utilization coefficient less than 1.0. For a probabilistic analysis of the same problem, we need to determine the mean values and standard deviation for the different parameters included in the limit state equation. The mean value and the standard deviation can be determined from the characteristic value of the yield strength with some assumptions. If we assume that the characteristic value for strength is given as the 5% lowest value in the distribution, the equation for characteristic strength can be written as the characteristic value of x being equal to the mean value of x minus 1.645 times the standard deviation of x. This can be rewritten to an equation as a function of the coefficient of variation by dividing all parts by the mean value of x. If we assume that the coefficient of variation, COV, is equal to 0.11, the characteristic value divided by the mean value is approximately equal to 0.82. And given that the characteristic value for the yield stress was 295 megapascal, dividing this by 0.82 gives a mean value for the yield strength of 360 megapascals. The standard deviation can of course then simply be determined by multiplying the mean value and the coefficient of variation to a value of approximately 40 megapascal. Similarly, we can determine the mean value and standard deviation of the load by the same method. However, for load we normally assume that the characteristic value of load is set to the 2% highest value of the distribution, giving us a 50-year value of the load. Performing the same type of rearranging and assuming a coefficient of variation of 0.3, the mean value of the load can be determined to 200 kilonewtons per meter. With this information, we can determine the mean value and standard deviation of R and S. We assume that the length, height and breadth of the beams are fixed value identical to what we presented earlier in this example. The mean value of the resistance R can then be calculated as the breadth times the height to the power of 2 divided by 6 times the mean value of the yield strength. And the standard deviation of R can be calculated as the breadth times the height to the power of 2 divided by 6 times the standard deviation of the yield strength. Similarly, the mean value and standard deviation of the load can be calculated. If we assume that all the parameters are normally distributed and independent, we can use the Cornell's formula to calculate the safety index beta to 1.55, giving a probability of limit state exceedance of 0.06 or 6%. A 6% likelihood of limit state exceedance or failure for a beam would normally be regarded as unacceptable. If these beams were in a building with 100 similar beams, this would imply that 6 of these beams failed yearly. A similar result was also indicated in our partial factor approach evaluation. If we, as we did in the partial factor approach, increase the height of the beam to 550 millimeters, we can recalculate the mean value and standard deviation of the resistance and load, and again use the Cornell's formula to calculate the safety index to a value of 4.34, giving a probability of limit state exceedance of 7 times 10 to the minus 6. Which is a significantly lower probability. We will get more into standards for probabilistic analysis later and the acceptance criteria for probabilities that these are providing, but just to give an indication. These are the target beta values given in Eurocode 1990 for different reliability classes, indicating a required beta value of 5.2 for reliability class 3, 4.7 for reliability class 2, and 4.2 for reliability class 1. Our beam, with an increased height, had a beta value of 4.34, which will only be acceptable in reliability class 1 according to this table.